So some of these chemical oxides are your friend, and they may help you from accelerated thermal erosion, okay? So what's thermal erosion? Well, like I said before, you're going to have, even though it only takes about a millisecond or a little more for the bullet to actually pass through the bore when you shoot, you're going to have a lot more gases flying out of there after. I mean, you still got that fireball following the bullet, right? So you're going to have superheated gases continuing to go for a little while longer, a couple milliseconds probably, from 1 to 5 milliseconds long. So you have this like almost instantaneous like increase in temperature from normal room temperature, especially on a cold bore, to 3,700 degrees instantly. And the sources from this heat obviously is mostly from the gas propellants, and also there's a frictional heat. You got the bullet sliding through that steel rifling, and that's going to significantly increase your heat as well. So what the result of this is, you're going to have a temperature affected zone. And this is going to be a couple hundred microns deep in some cases. And obviously this varies on what kind of steel you're using, what kind of cartridge you're shooting is going to have a huge effect on this. Your large magnum calibers with some of the serious overbore, like the more case capacity you have in relation to the actual diameter of the bullet, where you have a real big case that's neck down real far to a small bullet, you're going to have a lot more thermal erosion than some of the other cartridge cases. So like your 308 is going to have a relatively lower thermal erosion problem than is like 264, Winchester Magnum or whatever. So some cartridges are nicer than some for this. And that's why another reason when we talk about our reloading, and I'll refer back to this section when we're doing our reloading, you don't necessarily want the most hot load possible, right? Because you do have to deal with thermal erosion factors, and the more rapidly you erode things, the harder it's going to be for you to keep on top of it and correct for it when we're doing our long-range firing solutions. So you want to keep things mild, actually, if it's possible. So let's look at this here. We got instant temperature increase up to 3,700 degrees Kelvin. Well, basically, at the surface of the bore, that's only going to heat the actual steel up to 1,500 K. So half that, roughly, So you're still going to have a dramatic increase in the steel, but it's not going to be like the full 3,700 K. So you're going to have these temperature-affected zones, and they are going to run to a certain depth, and it's going to be a varying depth. And if the surface of your bore is changing, it's increasing up to 1,500 K, you got to consider if the properties of steel. And at 1,000 degrees Kelvin, that's actually enough for austenite phase transformation of gun steel. And that can increase also the oxidation of the iron as well. Austenite, I don't know if you know what I'm talking about, that's known as gamma phase iron. And that's when you have steel, when you start heating it up, you have the different temperature phases of steel, obviously up until it starts melting and things. But it's a metallic, non-magnetic allotrope of iron. I don't know if any of you guys hobby with blacksmithing or anything, but that's the temperature some guys like to heat it up to so that you can do your tempering, because that's when it changes the lattice structure of the steel when you're at that temperature, and you can start to change things. So austenite phase in steel is a significant phase transformation, and particularly when we're talking about introducing like a huge amount of mechanical erosion that we're going to have following along with this temperature change, right? So you're going to have a bullet rubbing past it. That's going to significantly affect things. So this basically is going to result in thermal softening in the austenite phase, obviously, of the steel surfaces, which is going to enable significant mechanical erosion, or what some guys refer to as a wipe melt process. So you're going to have this softer steel as it's real hot in the austenite phase, and that's going to basically be subject to, it's rare that you're going to get a full-on melt, but you're going to have a slight melt wipe process. And some guys think that this is crazy, the wipe melt process. There's different, mechanical engineers of gun barrels who disagree on this, if this wipe melt process exists. But if you're going into the austenite phase, you're basically going to have deformation, at least, of the steel that's being accelerated, because this does soften it. So you're going to have these cracked surfaces also with the temperature zones, right? And that's going to be vulnerable to mechanical erosion and accelerates chemical attack as well. So the thermal effects are pretty dramatic. And you're going to even have, even though at the surface you're going to have 1,500 degrees Kelvin, even 1 millimeter deep into the steel, just from at the instant of the shot, you're going to have an increase up to 370 degrees Kelvin. So it's a pretty good temperature gradient from the surface of the bore to 1 millimeter of depth. So you're going to have that thermally affected zone is going to be significant. And obviously, when you get inside 1 millimeter, it's going to be a lot less heat. So the outside of your rifle barrel, although it might feel hot, you got to know that during firing at the inside of the bore, that sucker is way hot. So just because you might not be burning yourself on the outside, it's going to be way, 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 way more hot on the inside of the bore, obviously. So something to keep in mind. And another thing that occurs, and we did discuss, or I did hint at it, is you have thermal shock. And that's basically a sudden, extremely steep temperature gradient from the bore to the cool part of the barrel, and that's what basically results in your cracking, especially in the chemically active zone where the steel's already kind of brittle. So you're going to have micro cracking. And also, if you look at it, you can see this sometimes a little more easily. You're going to have heat checking, and that's that alligator skin-like appearance. I don't know if you guys have seen pictures of heat checking. Some of the reloading manuals talk about that, but that's that alligator skin-like appearance that's basically forming from all the different cracks in the bore due to the erosion. So that's something you want to basically keep in mind. The next big thing we got to talk about is the mechanical erosion. And that's probably the dominant process for our purposes, for low-temperature firings. Because as precision rifle shooters, we're not going to be just blasting like through with a machine gun. A lot of this research, was done using machine guns, large caliber machine guns like 14.5 millimeter cannons, 50 calibers, and stuff like that. But for our purposes, we're talking long-range precision rifle shooting. You're going to take one shot, hopefully, and then hit your target, and then you're good, right? So in low-temperature firings, mechanical erosion is going to be a lot more important than it might be if you read some of the research papers on the other weapons. So we have the chemically degraded, thermally softened steel, and you're going to have all those surfaces that are starting to crack, and then you're going to slide a bullet through there that's really tight. It's formed to the rifling, and it's going to be ramming through there at 3,000 feet a second or so, or 2,700 feet a second, whatever you got, and that's going to cause significant erosion, obviously. And there's different subcategories of mechanical erosion. You could divide it up into, I suppose, like there's mechanical erosion that's actually due to some of the copper fouling that you experience from the jacket. And what happens is you can have some of the copper facilitates further cracking because it gets into those cracks, right? And then you have liquid metal embrittlement, which can happen, and that can accelerate cracking sometimes. You can have sweep and wash. That's basically where you have there's solid microscopic particles, or really not even microscopic, but really small particles sometimes mixed in with the propellant. And as that stuff burns and flies through the barrel, you could have like little tiny hard pieces that erode the bore as well, kind of like sandpaper. And that sweep and wash can really be a problem when you talk about jetting. Sometimes you have gases flow around the projectile. You have all that super high pressure behind the bullet, and the bullet's trying to build up speed. Well, the gas is trying to get past there, and sometimes it jets through any crack it can find. And that can really, really, where those cracks are, you have little jets. And that can exacerbate the erosive flow locally in a very small area. And in those localized areas, you can have increased erosion by 200 or 300% more than it would be normally. So any little tiny micro scratches you have in your bore or anything like that, that you're going to have locally concentrated jetting zones sometimes that can really cause problems. And this can accelerate erosion, particularly towards the end of a barrel's life. more than at the beginning of a barrel's life. And that's really what starts to render a barrel useless after a while, is once you start having significant gas leak around the projectile as it's moving down the bore, you have jetting. And you're not only going to have a loss of gas pressure and a loss of muzzle velocity due to that jetting, you're going to have less of that gas is being used to push the bullet forward. It's just burning a hole around the side of the bullet, and that's going to make a mess out of your bore. So that's kind of when you know your bore is done, is when you have a lot of jetting action going on, and that'll be marked usually by a wild inaccuracy or by a significant drop in muzzle velocity towards the end of a barrel's life. Now, for precision shooting applications, we usually don't let it get that far because you're going to notice a lack in accuracy due to some other things as well. So basically, you got those three different dominant processes. You got chemical erosion, thermal erosion, and mechanical erosion. And they all basically add up to just erosion. And the effects of bore erosion, you might notice that, per shot, you might only have, maybe a tenth of a micron per shot, or you could have up to 200 microns of bore erosion per shot. That's how much material would be removed each firing from the bore. So you have a huge range of how much this can affect it, from a tenth of a micron to 200 microns. Now, a micron's pretty small, so you're still going to have a couple thousand rounds of service life, but it tremendously depends on how you treat your bore. The cleaning regime you use, the chemicals you're going to subject it to, the gunpowder recipe, and a lot of it depends on how hot your cartridge is loaded. So we're going to talk about this in more detail in a reloading section, but you might not always want the hottest load, and this is one of the reasons why, and we'll talk about some of the others also. But how fast your rate of fire is, that can be a huge determining factor of how long your service life is going to be and how much erosion per firing you're going to experience. And if you look at where this erosion is distributed, here's a picture of the barrel, okay? And there's a graph above it that kind of shows greater erosion and less erosion, basically. And it's going to be the worst at the origin of the rifling, right at the beginning. And the reason for that, obviously, is it's going to be closer to where the origin of the heat is. The burning propellant is going to be the hottest at the cartridge, right? And as your bullet starts moving forward down the barrel, you're going to have an expansion. And we talked about Boyle's law earlier, how when you have more room, that the pressure decreases and you're not going to have as much heat concentrated in a small area. So as the volume behind the bullet increases as it moves down the bore, the heat's going to start going down. So you're going to have a lot worse erosion towards the chamber in the first part of that barrel, as represented by the graph here. And then you will have a little bit accelerated erosion at the muzzle, and part of that is because you have that extra surface area right at the crown of the muzzle where it opens up, and also you're going to have a little more turbulence in there. Some other weird things that go on. I could talk for a million years on this stuff, but let's try to get somewhere, I guess. So another thing is you got to consider is that these bore erosion effects are also going to change your muzzle velocity, and we'll talk about this in more detail in the muzzle velocity video. But basically, as these cracks start developing in the bore in the early part of the life, especially when it's still relatively tight, these cracks can actually expand the overall area that the metal is covering. So it might shrink your bore actually because it's cracking apart. So you might have, it's weird, if you take a bore measurement in the early part of a barrel's life, before the erosion starts really taking material away, your bore can actually shrink a tiny bit due to some of the cracking effects. And that can increase your muzzle velocity because you have less gas going around the bullet and because your pressure is changed. It's a little bit higher pressure. So your shot start pressure is what's needed to get the projectile moving. And if you change that, that can change your velocity. So basically, at the beginning of a barrel's life, when you have the cracking, some guys do experience a slight increase in muzzle velocity, and that's known as hump. We'll talk about that later, before the velocity starts to crash, and that's when you have the lower muzzle velocities due to erosion. When you have a loose bore, and your projectile's going through a looser bore, you're going to have more gas escaping, and that's not going to build up your pressure like you need to get her really going fast. So this not only affects the axis of the bore, like we said earlier, as this erosion changes the internal surfaces of your bore, that's going to totally change the frictional dynamics between the projectile and the bore. And those changes in frictional dynamics not only change the muzzle velocity of the cartridge, they significantly change the harmonic vibration pattern, particularly the whip action of the bore, which can change the axis of the bore at the muzzle at the time the bullet leaves the muzzle. So that's the main thing to take away from this whole story, is that your bore could be pointing a different direction than it was timed to your bullet exiting the muzzle. So as your bullet's leaving, it might be pointing a different direction due to a change in the harmonic nature of the vibration pattern. So how does a guy deal with that? Well, I'll show you at the end of this internal ballistics series how to put together a muzzle velocity curve, and we'll also talk about proper field deployment of how you want to treat your bore, okay? Some of the other effects that you might have due to bore erosion obviously is a loss in accuracy towards the end of the barrel's life, but you can have a compromise in the directional stability of the projectile, right? If you're rifling shot, it ain't going to be able to stabilize it very well as it's flying out there. And like we talked about, propellant gas blow by. You can also have, once you start having like excessive muzzle flash or really, really heavy blast going on, like if all of a sudden you got a lot of blast that you didn't have before, that could be an indication that you've had too much bore erosion, that your barrel's pretty much cached. It's done. So we will talk about muzzle velocity patterns here shortly in a couple videos from now. We're going to talk about the hump. That's due to the cracking and the rise in chamber pressure during the early part of a barrel's life. We're going to talk about how the muzzle velocity can increase for a short time as you're breaking in your bore. And then we'll talk about how it stabilizes and how your muzzle velocity patterns start to crash towards the end of a barrel's life. Couple more things we're going to talk about in this video is bore coatings. Some guys are asking about things like chrome lining and molybdenum coating on the bullets and things like this, and this is a good place to discuss that. Okay, target is definitely down, but I forgot to put on my earmuffs. Okay, looks like it hit a little bit low on the bottom edge. Target number 2. All right, on sight. All right, direct hit. Not bad. Okay. $890. Confirm.
Green light.
It's a hit. Hit.
1.13 kilometers.
Oh, you got it!
Oh.
Holy cow, you got it!
Indexing 20.36. We're going 20.4. Oh, yeah. Good call.